Okay, so this is going to be a little talk through of the problem that I've set you today. So hopefully you've had a look at this already. If you haven't, maybe just pause this YouTube clip and then open it up and have a look. So it's called a palindromic number. Now, a palindrome is a term we use for a word that can be read forward and backwards. So the word Otto, for example, OTTO, is a name. It's a European name. Otto can be written both forwards and backwards. Race car, the two words, they can also be, if you put them together, race car can be read forwards and backwards. So they're both palindromic. So palindromic number is a number that is written the same, or number that is the same when written forwards or backwards. The first palindromic numbers are therefore 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so the single digit ones. And then 11, 22, 33, 44, 55, and then moving up 101, 111, 121. As you can see, they will be palindromic numbers. So moving on from that, a number is considered to be double base palindrome if the number is palindromic in two bases. So for example, in base 10, 585, 585 is the same forwards and backwards. In base 2, it's 1001001001. So that's the binary equivalent. And if you look at that, you can see that that would be the same both forwards and backwards. So both the palindromic, and figure 1 shows the first 8 double base palindromes along with the binary equivalent. So we start off in single digits. 0, 1, 2, 3, 4, 5, 6, 7, no, sorry, 0, 1, 3, 5, 7, 9, and then binary 0, 1, 1, 1, 101, 111. You can see that there. Go into double digits. Now, going beyond that, then the numbers become quite large quite quickly as we go down, searching for the next ones in the series. So we want you to write a program that will check to see if a number is double base palindrome in base 10 and base 2. The program should be developed to list the first 20 double base palindromes, displaying them in the same way as the figure above. So I'm going to talk you through that. The way we're going to start doing it is to go over to a IPSO document, and the reason why I want to look at these is because this is the process you're going to use in your NEA when you start doing that. So it's when you look at a process and you break it down into its subsequent parts. So first off, in terms of the inputs, now I think for this one, the inputs are going to be numbers. So we're going to type in, or we're going to give it the numbers 1, 2, 3, 4, 5, 6, and so on, and get it to test those. And as it goes through, if it tests it and it finds out that if the denary number's palindromic, then it can go on and then check the binary equivalent. And if the two are the same, then we've got a match, and then we can store that. And at the end, we can output the 20 numbers. So the inputs are going to be numbers ranging from 1, 2, and then we don't know yet, but it could be just keep going until we have found 20 matches. So that could be a lengthy process. That's the only input, and we could generate a program to do that. So we could write a loop to do this quite easily, get it to count through and give us a number 1, then 2, then 3, just counting on that way. So the process is, so thinking through that, the process will be, you could have a pause and just think about that and then come back to this, and then you complete your chart and check your answer would be a good thing to do. So the processes are reverse a number and check to see if it is the same forward and backwards. We need to then, if there is a match, we need to check the binary of that number. We need to get the binary number as well, don't we? So we need to be able to convert the number to binary and check the reverse. And if it is the case, we need to be able to process will be add to the match list. And the other process will be we need to be able to stop at 20. So those are all the things happening. Check that against your list, see what you came up with. Now have a think about storage. Then when you've done that, come back to you can pause this and then come back to this. So storage, we're going to need to store the matches. This could be in a list. But we also need to do some temporary storage. So we'll temporary store in variables the values of the binary number, the denary number, the reverse, and the match. So this would probably be good to use as strings. This would be good to use as strings. So if you have a number, an actual integer number, it's harder to check it. If it's a string, you could look at each item in turn and then decide whether that's the same forwards as backwards. So that's all our storage data. Now what would our output be? I think that's a simple one here. The output is just going to be the 20 matches that we discovered. Okay, and then we'll print that to the string. So print to the screen. Okay, so we'll stop this one there. So that's the first part. We've taken the problem, we thought about it, we broke it down to input, process, storage, and output.